Hello, my name is Myung-Hoon Jeon. You can call me Philart. I'm working at Virginia Tech. This work has been done with my student, Shihab, and our collaborator, Dr. Ichi Zhang in Penn State. So I'm going to talk about computational modeling in auditory display. In human factors and engineering psych, there are three different levels of research approaches. The first level is psychological level. So we do experiment, human subject research. And when it comes to auditory user interfaces or auditory displays, we do usability testing. The second level is neurological. So we use neuroimaging techniques, fMRI, fNIRS, and EEG. The third level is computational level, but little research has been done specifically in our community, ICAD community. So I want to introduce you to computational modeling. Why computational modeling? There are benefits. So we can quantify how different design parameters can influence human behaviors more systematic way. We can simulate the dynamic state changes and we can predict human behaviors. If we use computational modeling, it's economical, it's accessible, and many times it's faster than doing research or experiment in the real world. Then why QN-MHP Framework? So that is Queuing NetworkModel Human Processor. So nowadays, many people do research using machine learning, which is bottom-up fashion. So machine learning is good in terms of modeling based on unstructured data, but there's no guarantee the model built based on the data has similarities to how our brain is working, right? So there are also more traditional top-down fashion in modeling, which is cognitive architecture framework. So QNMHP is one of these traditional cognitive architecture frameworks, such as ACT-R, APIC, and SOAR. So QNMHP is based on neurological and psychological data and theories, and its subnetwork is built to represent a refined auditory system structure, as you see in the next slide. And this is also good at simulating multitasking, which is good for dynamic situations like driving. And all the case studies I'm going to present today is in driving domain. Then what is Queuing NetworkModel Human Processor? Again, this is one of the cognitive architecture frameworks. So they assume the information processing based on three different subnetworks: perceptual subnetwork, cognitive subnetwork, and motor subnetwork. And under each subnetwork, there are many different processing servers. So depending on the characteristics of the stimulus, or maybe depending on the situations, the same stimulus can go through different routes, different servers, when that information entity is processed. So for example, let's say we want to get the response time. So here's response time equation. Some information can go through short route. So route 1, so it's quick and dirty. But sometimes, for whatever reason, our brain, specifically our cortex, has to scrutinize that stimulus. So thinking and identifying more in depth. Then that stimulus has to go through longer route, which is route 2. So how do we get this response time? All the subnetwork and server processes, so sum the time and multiply by the probability of each route. So let's say we are interested in this server 8, which is auditory recognition and location. If we advance or manipulate this server, then we can do research something like effects of the word choice in speech warning and lead time on perception. So that is actually the first case study which has been done by Dr. Zhang in Penn State. So she want to model drive response to collision warning sounds in connected vehicles. So they built the model based on literature. So there's a bunch of literature about speech warning, and you're probably familiar with these keywords, right? Danger, caution, and notice. Based on different word choice, the speech warning influenced perceived urgency. So they made computational modeling based on different word choice. So here's a couple of case studies we've done in my lab. So we wanted to model drive response to takeover request sounds in semi-automated vehicles. So in the first case, to get this perceived urgency, we used drivers' subjective rating scores. So rating score about perceived urgency and rating score about intuitiveness of the sounds. So we used those two parameters when we model perceived urgency. In the second case, second study, we replaced this warning urgency based on acoustic characteristics of non-speech sounds. So instead of this WS, we used warning urgency acoustic characteristics, and we included fundamental frequency, number of repetition, and pitch range. So that is another model about this takeover request sound. Then how do we build the model and how do we validate? So there are different approaches. We can build a model based on the literature, right? In human factors or acoustic research. So we get the numbers and quantification based on literature, or we can build a model based on empirical study. So let's say we do two different experiments. The data from experiment 1 can be used for building the model. The data from the experiment 2 can be used to validate the model. So we typically get two different numbers. So the first one is root mean square error, and the second is R square, so correlation. So as you see here in different research projects, we've got relatively high prediction R square. So we could advance the model using a variety of parameters, including objective data or subjective data about sound. And we could influence auditory, all kinds of auditory processing, perception, recognition, word choice, and other things. And we also showed relatively robust and reliable prediction values, over 90%. But if it shows like 99% correlation, then that might be overfitting. So we should be cautious. But when we built a model and then apply that to different situations, we also got like around 70% of prediction, which is good. Of course, there are challenges and limitations. So basically, following this fundamental assumption in cognitive psych, we just sum up, sequential temporal processing, but then that cannot explain parallel processing in our brain. Also, we cannot explain how different parts of brain can integrate different information pieces here and there. That's kind of hard to get at this point. And of course, we need more researchers and more data to make more model and validation. So nowadays, many researchers try to integrate bottom-up approach, so machine learning approach, and cognitive architecture approaches. So we call it hybrid. That's worth trying. And the existing model like ACT-R really focused on visual motor behavior model, but not really about audio. So we try to start to build a model in auditory display, and we can probably make or build different models about multi-modal interactions, not just visual, not just audio. And then we can also think about how this computational modeling approaches can be aligned with other traditional or classic research methods. Okay, so that's what I have today. Thank you for your attention. And I really hope this presentation and our paper can spark more discussions about computational modeling so ICAD researchers can utilize this computational modeling approaches in their research. Thank you.
Thank you, Fallard. And we have our first question, which is quite related to the question that I was having while I was listening. Prithvi asks, is there any way such a computational model can be used to simulate and quantify the meaning-making process that sonification listening usually involves?
Yeah, that's a great question, I think. So what we focused on in this stage was about perceived urgency. There are many reasons to focus on this specific domain, because to model based on neurological and psychological theory, and also we need cumulative data. The problem is, so about urgency, like we see from Penny's presentation, and we all know Edward is all kinds of research. So we have a lot of data. So we can easily build the relationship between perceived urgency and acoustic characteristics and people's behavior. So computational modeling is really making this relationship and equation, right, between these parameters. But if we think about general sonification, then that has way more parameters required. The problem is we don't have that data yet, right? So when we hear different types of sonification, how our brain is working, and then what would be our structured behavior, there's no answer about that. And there's no specific route about processing that, for example, like musical sonification. So I think ultimately we can get there, but still we need way more data and more experiments to make that happen.
Interesting. So what I was thinking about was kept reflecting on this top-down versus bottom-up approach, and of course, I'm not going to pretend that I understand the scientific and mathematical elements of your talk. I'm not going to pretend that, but I am fascinated by AI and machine learning, and I'm thinking, of course, when we think about urgency perception in a dynamic situation, like when you are actually driving, yes, laboratory tests are trying to simulate that situation with various other cognitive load tasks, and I understand that. But in the real situation, there's the alarm system, but there's also the soundscape that is happening around, and that probably, depending on how quiet or loud it is, it would have an effect on the perception of urgency, as well as the general mental and even emotional state of the person. And those are things that they're hard to create a top-down cognitive architecture for. But if there was data available about that was qualitative from situations where urgent response was required, you could integrate a machine learning algorithm that could be part of this hybrid system that you're talking about. Does that seem at all like a good idea?
Yeah, I think, yeah, definitely that's a direction. So nowadays, yeah, more and more people actually using machine learning approaches and bottom-up approaches rather than this traditional cognitive architecture. Like I said in the presentation, if we use this cognitive architecture, then because it's deeply rooted, right, from neurological and psychological research, so we can see and pinpoint what's going on in our brain or in our minds. It's great, but I mean, my answer is actually relevant to the first question as well. So because we have too many variables, right? And if we think about like emotional responses, way bigger, Pandora's box, right? So in that case, maybe machine learning approaches can be more appropriate. So maybe we can put parentheses, some of the variables we cannot explain, but still as a result, right? So we have black box here,
yes.
And then we have a bunch of inputs, and human behavior is kind of more structured. So that could be maybe more efficient ways to solve some practical problems.
Well, it's accurate. I mean, it's also about accuracy in the situation, right?
Right.
Yeah.